Hi, I'm going to show you how to calculate frequencies using the formula for the Doppler effect for both a moving source and a moving observer. Okay, so let's say that you're driving your car and an ambulance comes up behind you. There's our ambulance, and of course they're driving fast. Let's say that their speed is 30 meters per second, so about 65 miles per hour or so. And let's say you're still driving. Of course, you should pull over, but let's assume that you're not paying attention or something, and you're still driving, and you're at 10 meters per second to the right. So both of you are going to the right. The ambulance is behind you. So let's look at and want to predict what the frequency observed by you, assuming that the siren has a frequency, a source frequency of 1,000 hertz. Okay. So the general purpose formula for Doppler effect looks like this. So if we want to get the observed frequency, it equals the source frequency, and you'll see different ways of writing this that are probably correct, but this is how I do it. So 1 plus or minus the observer's velocity divided by the speed of sound. So the v without a subscript here is the speed of sound. And then we have 1 minus or plus the speed of the source over the speed of sound. So you got to be the only really tricky part of this is to deal with the signs of these things. So the plus and minus here is towards and away. So positive if it's towards, negative if it's away. And then the sign convention gets flipped for the denominator. It's negative if it's towards and positive if it's away. Okay, so we're used to, with kinematics, the idea that the plus and or in forces and just about everything else, that the plus and minus come from the coordinate system. Okay, we're going to say the right is positive, and then both of these would be positive or something like that. But don't you have to throw out that thinking and think in terms of the towards or away as opposed to a coordinate system. Okay, so in this scenario, go ahead and just chuck numbers into the formula, apply the correct sign so we can predict what the frequency observed is. Okay, what'll that be? Okay, we can calculate it. So just throwing numbers in this formula and throwing signs into that formula. So observed frequency will be, okay, source frequency of 1,000 hertz times 1 plus or minus. Okay, so the plus is towards, but the observer is going away from the source. Okay, even though the source is catching up, they're driving away. Okay, they're not driving towards. So we put a minus sign for going away. So 1 minus, and then we have their speed 10, and then okay, we don't know the temperature, so this isn't a perfect calculation, but kind of this, we typically use 340 or 343. I'm going to use 343. But if this was a cold winter day, this would be wrong. We want to use something closer to 330. Okay, then we throw in 1, and then we got to decide on the sign for here. So the top one is towards, so we actually put a minus sign in the denominator as well. Okay, and just looking at this and kind of thinking about this in terms of the numbers, this number is going to be smaller than this number, and we're going to have a ratio that's above 1, and we're going to get an increase in the frequency observed, which I think is intuitive here. The ambulance is catching up to the car, and so the observed frequency is going to be higher than the source frequency. Okay, so observed frequency, we do end up with 1,063 hertz. So this person hears a slightly different pitch than the person inside the ambulance, and that's the difference there. Okay, so and I'm going to follow this up with, well, what happens after the ambulance passes? Okay, we can deal with that as well. And you might, while I'm doing this, you might try to think about what signs would you use. Okay, really it's just a matter of chucking in numbers. Everything's pretty straightforward except for this weird sign convention. So let's try this again after, so let's say the ambulance is over here, past the car, still going at 30 meters per second. Okay. So using the same formula, we would have source frequency of 1,000 still. Okay, 1 and then we'll do 10 over 343, 1, and 30 over 343. And now I want you go ahead and pause the video and decide for yourself what signs you would put in here. Okay, so the observer is now moving towards. Okay, so the ambulance is over here. The car is moving towards the source of the sound, so we get a plus there. Okay, and the source of the sound is moving away, which is the lower symbol here, so that's also a plus. Okay, and so we're going to get a reduction in the frequency that's observed, and I get, when I throw those numbers into my calculator, I get 946 hertz. Okay, so it's not exactly symmetric. It's tempting to think, oh, okay, it goes up by 63 hertz, so this one should be 63 hertz less, but it's not the same thing. It's 54 hertz less. So yeah, don't necessarily fall for that type of thinking here. Okay, so that's it. So just, yeah, only tricky thing here with these types of problems is to make sure that you get the sign right, thinking about towards or away as opposed to a coordinate system. And then of course you sometimes have to infer what the speed is. So based on the properties of air, which is typically how the sound is transmitted, you should be able to determine what V is. Okay. All right, that's it. So thanks for watching. I'll see you next time.